Hey everyone, and welcome back to Prefusion. So today we'll study a new concept of control systems from state space analysis topic. So I have briefly explained about this topic in my full course. You can watch this here, like in lecture 13 in YouTube. It is present there. I have explained this, okay, about the state feedback. So someone from our Telegram group has sent this question, and I saw this new topic, and generally students tend to skip this topic, and teachers also generally don't teach this particular topic, right? Even though I have explained a bit about state feedback, no other teacher has explained in this much of detail about state feedback in any of their full courses. I know this very well. Okay, so this question is basically given: a state space representation is given, and you have to find out the state feedback matrix that changes the location of the poles. Like currently the location of the poles are somewhere else, and it wants us to place the location of the poles at -1 and -2. Exactly, we want our poles to be at these locations. So this particular method is very helpful if we want to specifically place our poles right at some locations. Okay, that's why we use state feedback. Obviously we can't directly solve this. First of all, we have to understand the few concepts, then we will solve this question at the end. Okay, so like here also I have explained about feedback, state feedback, all these things in a brief. Okay, you can go and watch my state space analysis lecture 13. At the end I have explained a bit brief, but here we'll go more in depth, okay, of the state feedback. So first of all, what does state feedback means? State feedback means that the state measurements can be used to determine the control action. So basically we're taking the feedback of the state parameters. So here is my state variable, right? Here is my state variable. Okay, so like this is the, if you observe this correctly, if you just skip this part, right, and if you just focus on this is basically what? This is basically the block diagram representation of state space matrix. All this I have explained in my full course, so I will not go much in depth of this, right? I have explained in my full course. So this part is the block diagram of state space representation. Okay, what is the state space equation? State space equation is basically this. I will write the state space equations. So here, first of all, this is without feedback. That is basically it is talking about when k is equals to 0. Then what are my state space equations? So first of all, my u of t, right? U of t is this. U of t is this, right? This one is u of t, and k is 0, right? No feedback is coming. So r of t is directly equals to my u of t. R of t is directly equals to my u of t. And what will be my x dot of t? X dot of t, if you observe very carefully, is basically two things are getting added. This a times x of t and plus b times u of t. So a times x of t plus b times u of t. And what is my y of t? Y of t is basically x like c times x of t. Y of t is c times x of t. Obviously we are ignoring for now the d matrix, right? We are assuming d is a null matrix. Okay, so here, right, these are the state space equations. Okay, state space representation of a system, and this is basically the block diagram. We established this. Now this is without feedback. Now if I provide a feedback, right, which takes in the state space takes in the state state variables. Okay, if it takes the state variables as its feedback and it feeds it back, okay, to the input, and it is a negative feedback, then what will my state space equations become? Let's do with that. So this time we will write the state space equations with state feedback, that is my k is not equals to 0. Okay, so if k is not equals to 0, then u of t equals to, here, right, two things are coming in now, u of t. So this x times k, like k times x also is coming, and r of t is coming. So u of t has changed now. U of t is r of t minus k times x of t. And what is my x dot of t? It is the same thing, right? It is the same thing, that these equations are same. These equations aren't changing. These equations are same. But the difference is, I forgot to do one thing, that I have to further simplify this in terms of input, right? U of t is not the input, r of t was the input in our case. So u of t is equals to r of t in the first case. So it will become x of t plus b r of t. Okay, now this is my state space equation. Okay, now in this case what is happening is that u of t is equals to r of t minus k x of t. So this will become a x of t plus b r of t minus k x of t. U of t is this, right? So basically what does my state space equation becomes? So this x dot of t, I can write it like this, that it will be a minus k times b is also there, right? K times b x of t plus p r of t. So what I am observing is my system matrix, right? System matrix A has changed from A to A dash. So A dash is equals to A minus KB. So system matrix has changed. So if my system matrix has changed, what can I do with it? So basically, if I can change my system matrix, I can change the pole locations of my system. So if I can change the pole locations of my system, obviously it will change the behavior of the system, and what basically time domain response I want, what frequency domain response I want, I can control that, right? I can control that with basically this state feedback. So here I have written few points. Impact of state feedback on system. Feedback changes the behavior of system by changing the location of closed loop poles, as explained. In state feedback, the following analysis is made. Basically, how do we analyze? Basically, analysis means like how do we find out this state matrix? This state matrix, right? Feedback matrix. So basically, our A changes to A minus KB into X plus BU. Now this is how we analyze. So first of all, we get our desired location of poles, and with the desired location of poles we can find out the system matrix, and we can compare these two system matrix, our desired system matrix and the current system matrix which we have with state matrix, and from there we can find the state matrix. We'll do one example, they will understand. Okay, so like here I have told like the difference between open loop and closed loop. If we have open loop, then our state space equation for the first equation, okay, is simply this: x dot equals to ax plus bu. But if we have a feedback, then our equation becomes, this is actually r of t, sorry. Okay, then if we have feedback, then this becomes a minus bk x plus b r of t. Okay, so this is our x dot of t, and this is our normal with and without feedback. We can observe we are changing the system matrix, and if we are changing the system matrix, then poles of the system are eigenvalues of a minus bk. So eigenvalues of the system matrix, so we can change the location of poles with the help of state feedback. Basically, this is what the main difference is, and this is what we'll use. Okay, so first thing is, yes, it is clear that we will change our like pole locations with the help of the state feedback. But is there any good methodology to it, that precisely can I decide what will be my K matrix according to my pole locations? Can I do that? So first of all, if my this A and B, right, if my A and B matrix are very arbitrarily chosen, then it will be very difficult. Okay, it will be very difficult to place my poles arbitrarily. Why? I will just explain in the next slide. The calculations will become very cumbersome. Okay, and is there any systematic design method for selecting the feedback matrix K? That also I will tell in the next few slides. Okay, so first let's do one example and let's get a feel of it. Okay, so the state space representation of a system is given like this. Okay, and they have given the equations. Okay, they haven't given us the output equation, and we don't need the output equation, we just need the this first equation, right? So find the location of closed loop poles of the system with and without the state feedback matrix. So like we're just understanding that what difference does a feedback make to my system, state feedback make to a system, to the closed loop poles. Let's see, if I add a close like state feedback, does it change the location of poles or not? Let's see. So here they have given me the system matrix, and I know that without feedback, right, without feedback, basically the determinant of the characteristic equation, okay, of system matrix will be my characteristic equation of the system, and from there I can find out the poles. Basically it is determinant of Si minus A, if we remember correctly, all about state space equations. So in our case it is S minus 1 minus 2 minus 3 S minus 4 whole determinant. Okay, and we have to equate it with 0, right? Si minus A determinant equals to 0. So what will be this? This will be S minus 1 into S minus 4 minus 6 equals to 0. So it will be S square minus 5S plus 4, and this will be minus 2, right? Minus 2 equals to 0. So currently where are my poles located? So just hold on, this is minus minus plus, right? Yeah, this is minus minus plus, and this is minus, and yeah, Si minus A inverse. So all of these are fine. So where are my poles located? My poles are located minus B, so plus 5 by root 2. So just yeah, plus 5 plus minus under root B square. B square is 25 minus 4AC, so it will be plus 8 divided by 2A. So these are my pole locations, right? So SP is equals to 5 by 2 plus minus this is almost 33 by root 2, 33 by 2. Okay, so these are my pole locations basically. Now what I notice from here is, let me just quickly multiply these two if I am getting the correct answer or not. 25 by 2 and minus 33 by 2, no, 33 by 4. Okay, minus 33 by 4, so it will be minus 8 by 2, minus 4, fine, minus 4 is fine, 8 by 4, so minus 2 is fine. So like these are my closed loop poles, and I'm observing that they are lying on the right hand side. Now if I add a state feedback, will they shift my pole to the left hand side? That we'll see. Okay, so basically, is state feedback helping in stability or not? That also I have explained in my full course. Here if you see, I have explained when we are studying controllability. Okay, I have explained that state feedback helps to make the system stable. Okay, stabilizable. So here like we are doing this example right now with feedback. My system matrix becomes what? System matrix A dash becomes A minus BK. So A is what? A is basically 1 2 3 4, 1 2 3 4, and B is basically 2 1, and K is 0 comma 1, 0 comma 1. So this will become, first row will become 2 and 0 and 2. So this will be 1 0, and second row will become 0 and 1. So this will be 3 3. Okay, so this will be my new system matrix. Now what will be the characteristics equation? Characteristics equation will be Si minus A dash determinant equals to 0. So it will be S minus 1 0 minus 3 S minus 3 determinant equals to 0, and what will be this equals to? This will be S minus 1 into S minus 3, and this will be equals to 0. So this time my pole locations are what? This time my pole locations are simply okay, S equals to 1 and 3, although they didn't move them totally to the left hand side, but at least like they were trying to move it left hand side, and at least we can observe that yes, the pole locations are changing. If I had have chosen a better state like feedback matrix, I would have made them to the left hand side, but I didn't thought of that at this point of time. Okay, so let's go to the main topic, that is like impact of state feedback. Okay, if you want to study the impact of state feedback, so in principle we can now choose parameters to get desired pole. Okay, at any location we can get, but computation becomes very cumbersome if matrix A and B are any arbitrary matrix. So here A and B are like A and B are these matrices, and if I want to compute K for K1 K2, right, the characteristics equation will become something like this, right? I can observe these equations are becoming very untidy. Okay, very cumbersome. So like the pole locations will give me a characteristic equation, desired characteristic equation, and with this characteristic equation I will compare those two and I will equate the coefficients, and then I will get my answer. But for second order I can already see it is becoming very cumbersome. For third order it will become more cumbersome. Okay, to compute this in pen paper, that will be very difficult. So in exam all this won't come. Okay, but in exam what may come? In exam they can give you controllable canonical form, and in real life also sometimes what we do, we convert our system to controllable canonical form, and then we use the state feedback, because the computation for computing the state feedback matrix, when the system matrix is in controllable canonical form, when basically the state equations are in controllable canonical form, is much reduced. Computation is much easier. So what is controllable canonical form? I have already taught this in my full course, but just to give you an overview, like if your transfer function is something like this, right? Transfer function is something like this. This is not y of s actually, sorry. This is t of s. Okay. transfer function is something like this, and this is your denominator. This is what? This is the characteristic equation. So in controllable canonical form, what happens is we write the negative. We basically write the negative of the coefficients starting from the one coefficient, one order lower than the highest order. Okay, s raised to power n minus 1. So we write the negative of coefficients, right? Negative, and not this, right? So we'll go until a0. Okay, the zero order term. Okay, in negative. And what about my B matrix? So B matrix is basically a fixed matrix that will be like first row will be. So the first row will be something like this for the A matrix, and all the other rows, right? This will be 1. Okay, it will start from the second row. The first element will be 1. Then all the other elements will be 0. In the third row, the second element will be 1, and all the other elements will be 0. In the fourth row, the third element will be 1, and all the other elements will be 0. Okay, according to that, my this controllable canonical form is made. Okay, so in the last element, similar things is happening. And this is my A matrix. My B matrix is the first row, okay, of my B matrix will be 1, and all the other elements will be 0. And for my C matrix, the elements will be basically, there will be no sign change, but the coefficients will be something like this, right? B of n minus 1, B of n minus 2, up until B of 0. Okay, but do remember here, this is a proper transfer function. This format is valid only for proper transfer function. Okay, so these are the few formats, but mainly we are interested in A and B. Okay, C we are not interested in. Okay, so in controllable canonical form, the eigenvalues / location of the closed loop poles are determined solely by the parameters along the top row of the A matrix. Okay, along the top row of the A matrix. That is how my characteristic equation is written. As we can see, right, the characteristic equation we can write from this, just the top row. Okay, so if I have a state feedback matrix, okay, of n order, and bk will be what here, right? Bk, basically the first element is only 1, other all elements are 0. So basically all of this will be zeros, just the first row will be k1, k2, kn, right? 1 is getting multiplied to the whole row. So now if I do a minus bk, right, if I give it a state feedback and a minus bk I do, then this element, right, in the first row will be simply minus a n minus 1 minus k1 minus k2, like this, right? All the elements will just be subtracted by their corresponding state feedback matrix elements. Okay, and the other elements, right, they will remain unchanged, they will not change at all. Okay, so still this is in controllable canonical form, CCF. This is in still controllable canonical form. Okay, so that hasn't changed. So this is the characteristic equation. Okay, and these are the coefficients of individual terms, right? Coefficients of individual terms of the characteristics equation. Okay, so we can choose the location of closed loop poles by directly choosing the parameters of K individually by matching with the characteristic equation of the desired system by matching with the coefficients of characteristic equation of desired system. So like, what do you mean by this? Let's take an example. So a third order system has pole locations -1, -1, -1. It is desired to keep the poles at -1, -2, -3 with the help of state feedback. Thus feedback matrix K will be. Okay, so they haven't told us anything about the system matrix or anything. They have just told us the pole locations. So we will assume that the system matrix is in controllable canonical form. Okay, the state space equation are in controllable canonical form. So basically, what is the characteristic equation? All the pole locations initially are located in -1 only. Okay, it is a third order system and all the poles are located in -1. So basically, characteristics equation without feedback. Okay, so basically it will be s cube plus 3a square plus 3s plus 1 equals to 0. Okay, so this is my characteristic equation, basically s plus 1 whole cube, right? So for this, what will be my system matrix? My system matrix will be simply, it will be -3 -3 -1, then 1 0 0 0 1 0, right? So this will be my system matrix. Okay, so now like what we can do is we need to change the pole locations. We need to change the pole locations to this, right? -1, -2, -3. So what will be the characteristic equation for that? So characteristic equation for that will be s plus 1 s plus 2 into s plus 3 equals to 0. This will be my characteristic equation. Okay, so this is basically s plus 1. I will do this first. S square plus 5s plus 6 equals to 0. So this will be basically s cube plus s cube plus 5 s square plus 6s plus s square plus 5s plus 6 equals to 0. S cube plus this is 6s square plus 11s plus 6 equals to 0. Okay, so this is my characteristic equation of my desired system, of my desired location of poles. So for this I have to compare this with the systematics. So for this, what will be my systematics in controllable canonical form? So for this particular thing, right, my system matrix will be -6, -11, -6, and all of this will be 1 0 0 0 0 not 0 0 0 1, right? This will be my system matrix. Okay, so now what do you observe? If I apply a state feedback to this, if I apply a state feedback, what will change? So with state feedback, just hold on, with state feedback, okay, with state feedback, basically my system matrix A dash will be A minus BK. Basically it will be, the first row will just change, right? The first row was -3 -3 -1, so now it will become -3 minus K 1. Okay, then -3 minus K2 -3 not -3 -1 minus K3. Okay, so just hold on, like, am I writing this K1 K2? Yeah, this K1 K2 is correct only, because K is from there, so it will be K1 K2 and it will be subtraction. Yeah, so this, right, and this will not change at all. This will be 0 1 0. Okay, so this will not change. Now I have to compare this new state matrix, okay, system matrix, with this, right? So this should be same. So 3 minus K1 should be equals to -6. So I can say that -3 minus K1 should be equals to -6. So K1 equals to 3, right? K1 is equals to 3. Now also -3 minus K2 equals to -3 minus K2 equals to -11. So this is -11. So K2 is equals to 8, and the third equation is -3 -1 minus K3 equals to -6. So K3 equals to 5. So I can observe, just with like single computation, right, just with solving one equations, I can directly solve for K1 K2 K3, and like I can directly solve for the state matrix that is required, state feedback matrix that is required to basically change the pole locations to my desired pole locations. Okay, so this is 3 and this is 8 and this is 5. Okay, this is my feedback matrix that I need to place. So easy, right? So easy. So like with this is the system that I was talking about. If you have a controllable canonical system, then you can simply just write this and just compare the first row with the desired characteristic equation, and we will directly find the values of K, right? State feedback matrix. Okay, so let's come back to this question. This question wasn't with controllable canonical form. This question was any arbitrary matrix. So if it is 2 cross 2 matrix, right, then computation is pretty simple. Okay, you can do it with either that basic method that I taught you just before this, or using controllable canonical form also. So this also we can convert into controllable canonical form. I will show you how. Okay, but before that, let's solve it normally. So if I solve it normally, basically what will happen is I will choose a state matrix K1 K2, right? State matrix is K1 K2. So basically my BK is what? B is this, right? 1 0 1. B is 0 1. So this will become 0 comma 0 and K1 K2. Okay, so my A dash, what will my new system matrix become? So new system matrix will be A dash minus BK equals to this, right? Equals to so A is this 0 1, so this will be 0 minus 0 and 0 minus, like 1 minus 0, so 1. This will be minus 1 minus K1 and 0 minus K2, so this is minus K2. Okay, minus K2. Okay, so this is my system system matrix. So what is the thing they have asked us? They have asked us to place the poles at -1 and -2, right? So basically, what is the characteristic equation for this? The characteristic equation for this is simply, like, I can, for a second order, I can directly write that it is S square. Wait, I'll change the color. S square minus trace of A, which is plus K2S, plus determinant of A, which is 1 plus K1 equals to 0. So I can write it directly without going into that in between state, right? And what is my desired characteristics equation? So my desired, this is my actual and this is my desired. So now my desired characteristic equation, basically the pole locations are -1 and -2. So what will be the characteristic equation? It will be S square minus sum of the pole values, which is -1 -2, which is -3, minus of minus is plus 3s, then plus multiplication of the pole values, which is -2 into -1, that is plus 2 equals to 0. So I can directly compare, right? I can directly compare. Okay, I don't need to go to the method, that method. So it will be simply K2 will be equals to 3 and 1 plus K1 will be simply equals to 2. So K1 will be equals to simply 1. So what will be my system matrix? Now state feedback matrix K. So my state feedback matrix will be simply 1 comma 3. K1 is 1 and K2 is 3. Now if you want to solve with method 2, right, using the controllable canonical form, so first of all you have to convert this matrix A into controllable canonical form, then only you will be able to do it. Okay, how to convert all this I've explained in my full course from control systems. You can go and watch there. Okay, how to convert any matrix to controllable canonical form, and then you will solve using the method that I told. But for 2 cross 2 matrix, you don't need to do it. We can solve it using simple this method, right, basic method. But for 3 cross 3 matrix, you may need to do it because the computations will become more and more cumbersome and tougher. Okay, so GATE hasn't yet asked from this topic, okay, of state feedback, but I'm pretty sure in the next few years they will 100% ask from the topic. Okay, and this is a very, very important topic, and no one in the GATE industry has taught this topic. So you should definitely cover this topic, and I'm pretty hopeful that in the next few years they will ask one question from this topic. Thank you for watching, and I will see you in the next video.